So now I want to look at like running software. And why I want to mention this is I don't want to just talk about running, like we're going to start looking at running programs on my laptop, but then running them on an embedded system as well. So this is something that is generally, I feel, not really talked about. I mean, we don't have to go into super detail, which we won't really, but just understanding how you go from writing your C code to actually running a program on your embedded system, because you're going to be learning about system architecture and you'll get an idea of how assembly instructions are actually executed and what really happens on a CPU to make a program run. But there's always like a few missing spots, and one thing really is this process of getting your code that you wrote on your computer to be executing on your microcontroller. And so we're going to go through this like kind of quickly now. First, we're going to look at just compiling for our laptops, because it's simple and it's also something I feel that really helps to just clarify a lot of missing, or just to provide a lot of missing information to sort of beginning computer scientists. And it also makes a lot more sense than when we're talking about this embedded system sort of execute or boot up process. So what happens when I run my program? Like, how is your program running on my laptop? So I mentioned in this compiling, at the very end of the compiling lecture, that we end up with this this object file, this linked object file, or an executable file called an ELF, which I'll refer to now from now on as an ELF file. And how is this file structured? Because it needs to be structured in a specific way such that the operating system, in our case, or for instance in my case, my Linux GNU operating system knows how to actually execute and bring this program onto the CPU and get it to run. And so there's a lot of sort of standardization around this, and as we'll see, there's a very sort of tight structure to these programs that has been standardized over a long period of time, such that I can run my program on my laptop and you can run on your laptop. I could send it to my colleague and you run it on his laptop, you know? And so just going into this now, just sort of, you might get a bit confused, like, hey, I haven't seen this very much, because I think most students at the beginning of their bachelor and their bachelor time are usually dealing still with Windows and these sort of operating systems. So I'm talking about here, for instance, running and compiling on a Linux machine. So on a Unix-based machine, because I find the Unix machines, they provide a lot more transparency with this. And what I mean, they provide complete transparency. And so I think they're really easy to look at and to get an idea of what's going on. So for instance, at the end of our compilation process, we get this ELF file, which was generated by GCC through like make utilities or CMake units. So this is what we end up with, this ELF file, this executable and linkable format. And so what is it? Essentially, this ELF file, I mean, it's got lots of different sort of file extensions. It might be a .bin, .so, .ko even. And so what they are is essentially, it is a standardized binary file that's been standardized for Unix systems. And so for those people that don't know, like, Unix is essentially a standard, or it's a type of operating system that's been around for a long, long time. And it's essentially defines what's called syscalls, or how the basic operating system should be structured, such that it sort of enables standardized operating system interface, or allows for programs to be more easily run on different systems. And so Linux is a Unix-based system, similar to like Mac OS is also Unix-based. And so there is a little bit of sort of crossover in the sort of structure of like Linux and Mac, for instance, right? But essentially, the standardization, or the file structure that I'm going to be looking at, is specifically for Unix systems on an x86 processor. And so an x86 processor is essentially the processor architecture that is inside of my laptop, inside of probably all of your laptops, like AMD's and Intel's, whatever, these standard laptops that you have on your desktop or on your laptop. These are x86. And so this is generally it's just the architecture that means sort of general purpose computing, servers, whatnot. You know, it's not like a mainframe or an embedded system. So then we have this ELF file, and we know what system is going to be running on. But now we need to sort of break it up, and there's lots of different variants of this system. For instance, you have 32-bit systems and 64-bit systems. I mean, 32-bit laptops are pretty rare nowadays, like they'd be very old, but they do still exist. And so the ELF file needs to provide sort of information on like the type of file it is. Like, hey, is this designed to run a 32-bit system? Because you can run 32-bit programs on a 64-bit system, but there are some extra things your or libraries and things that your kernel or the operating system needs to take care of to make sure that this can happen. But the basic structure of an ELF file is that you have this header, which sort of tells information or metadata about the file itself, and it's sort of a standardized little like chunk at the top of the binary that the operating system knows its structure and can go and be like, yep, read this byte and knows the exact thing. And then there's the file data, which is a bit more, it's like more loosely structured because it might be a different type of program. It might not just be a C program, it could be something else, right? But some things that the header file, the ELF file we'll talk about, or the sort of format of it, is 32 bytes. It identifies the file format, specifically sort of like the interpreter that needs to interpret it. Like if it's a C file, then it actually get invoked by the like glibc interpreter essentially. And then for instance, sort of things like the byte endianness of the system, like is it little endian, is it big endian, what sort of OS does it target, and these sorts of things, right? And so it just provides a lot of like sort of information. And we'll see here, one thing that's also sort of fun about an ELF file is that the first, like not the first byte, but these second, third, and fourth byte, they'll spell out ELF in ASCII. And then you'll see here we have essentially, these are the 32 bits, and they show all the different sort of things that happen in the file, right? So this is all the information from my, I think it was my Hello World example. If I use readelf, which is a binary sort of dumping utility, it shows me all the different information, so that it's designed for a Unix system, system V. It's a little endian system. I'm running a 64-bit system, or it was compiled for a 64-bit system, which you can also see here. So it's an x86 64, right? The entry point address, and so this means, as we'll see in a second, this is where it can actually enter the program and finds the, like as you wrote, you can make main.c, and this is sort of how it gets into it. It also gives information on like sort of the size of the program, these sections, which we'll see in a second, and what they are and how big they are, and sort of tells the program where to go to find what things. Because then, so this is the header and it's telling us where things are. Inside the program itself, so inside the file data, we have a lot of different things which store different values and whatnot. But what they can include is essentially this program header table, which will describe these segments, like this, not just so much the text, but it's more so like the actual memory chunks. And so if we look back here, segments, or is it just sections? Yeah, so the sections here, it will show how big each section is and the program header here and where to find it, right? Oops. And so then the section headers, which describes, hey, we have like the text, the read-only data, which we'll see in a minute, as well as the program data. Yeah, we'll see this all in a second. I'll go through it in sort of a bit more detail. So we have like these memory segments. And so what a memory segment is generally used when we're dealing with sort of like memory structure. So not so much like what is stored in the sections, but the segments are sort of similarly to like pages of memory. And so on an embedded system, memory segments can be very important because you have different types of memory. Like you'll have read-only memory, and then you'll have read-write memory, so like flash and RAM. On like an x86 laptop, it's generally not as important, but it's very important when it comes to actually dealing with memory addresses and offsets because of how things are structured in memory. So this is not so much so important for us. What we're really interested in are memory sections. So the memory sections are essentially ways that the compiled data from the program is structured, in that all of the, for instance, the uninitialized variables all end up together in one section. The code ends up in another section. The initialized variables end up in another section. And so the compiled code is sort of sorted and structured in a way such that the program knows where to go to get what things, right? And so where each of these sections is located, this is defined by the section header, which we will see is here at the bottom, right? And so the section header is talking about like what sections we have. It's sort of saying all the information that's in the object file and where it is and what sort of sections it's in. And so the different sections that we have, or there's sort of like a number of standard sections, and some of the big ones are this BSS.data, ROData, text, and interp. So these, for instance, which we'll see in the next couple of slides, they all play a very significant role into getting your program to load on your computer, right? During the loading process. And so these special sections, or like these system reserved, meaning you can't tell your compiler or linker to create a .bss section, it's reserved for the system. Like the .bss section is very, like one of the more important ones, in that it holds uninitialized data. And so during the boot process, this also plays an important role because the system will generally initialize the stuff here to be 0, which is sort of like a safeguard. And so if I'm running my Hello World program and I have some variable in there that I've created that I did like int foo, but I didn't give it this equals 2, this is uninitialized. And so this, once this program is compiled, this actual variable's location ends up in the BSS section. Because these are all handled slightly different during the program's boot. Namely, the BSS section goes through this 0 initialization stage, is generally, as far as I'm aware, one of the only sort of differences. The .data section, now this holds as initialized data, which sort of makes sense. Like you're telling, hey, this is my data, these are what my values are for, and so like the name sort of makes sense to me, right? And so this is where initialized data is stored. It's obviously not zeroed out during program start because it's already got values. Now, ROData is, is read-only. So whether this is actually on read-only memory or not, this is sort of hardware dependent and all of this sort of stuff, linking dependent. But the ROData also plays an important role even on my laptop, in that you place values in there that you don't want to change. And so the compiler and the execution of the program will generally make sure that this doesn't happen. Like if I have the value of pi, I don't want it to be changed. But the values here, for instance, if I made a variable called const int pi and I set it to 3.14, then it would land in the ROData, and it means that it's a read-only value and it can't be changed during program execution. Oops. Now the actual code of the program, this is in the .text section. And so the text section actually holds the code instructions of your program. And it's generally stored separate to the data. Like it's clearly sectioned off in its own section, right? Now, one other sort of section that becomes important, which you won't actually deal with much when it comes to the whole like compilation process, in that when I'm debugging an object file, I'll be generally looking at these BSS or data files. Like sometimes embedded systems is really important to find out where your variables landed. For instance, if I have a large constant array, I want to make sure it lands on my ROData, because maybe my ROData is getting put onto my flash and I'm on an embedded system with not much RAM. So I really want to make sure that this constant variable is not landing on RAM. And so I'll go through and debug my object files to make sure that everything is where I want it to be, right? But the interp section plays an important role for like my laptop program execution, in that it holds the name of the program's interpreter. And so on my computer, on my Linux system, this is the LD, essentially the dynamic linker, or I can't remember what it's. Let's have a look. It's called dynamic. Okay. Strange. Yep, dynamic linker, right? And so we'll get into exactly what this does in a minute. But what's important is that it holds, or it tells us how we go about starting up our program, like what part of the kernel is responsible for doing this. So then we'll sort of look at like, how do we go about loading a file on my laptop? We know we have these sections where all my different data lives. We have this elf file header, which sort of tells us like, yep, okay, we have a little endian, big endian. It's a 64-bit program for a Unix system, meaning that all the syscalls should have the Unix standard. But how do we actually go about loading this into memory and getting it to run on the CPU? So to do that, the kernel of the operating system, which we haven't talked about yet, and we'll really talk about when we talk about real-time operating systems, it's responsible for doing this. So a 2-sentence summary of the kernel, or what it is: it's the piece of software underneath the graphic programs of your laptop that manages the hardware. It creates the interface between the software world of your laptop and the hardware world. Make sure that the CPU's running, that your memory's running, that your screen's running, and that when you start up a game that everything's good, that there's RAM ready and that your graphics card knows how to function, right? And so this is the kernel. It's a very low-level piece of thin, small software that runs on top of your CPU, and it's responsible for then obviously putting a program onto your CPU. And so it needs to do this, and it does this in a couple of steps, namely that it opens the file. So as you can imagine, you need to take the file from like your hard drive and put it into RAM, like to make it on the system memory so that it's accessible by the CPU. And then you actually need to execute the code, which we can imagine lands in this .text section. And then once this code is executed, then the CPU will actually start to execute the instructions of your program, meaning that the CPU or the program has control of the CPU. So this first step of a file, right? Essentially, we have all of these different sections which we talked about, and these are all unloaded into memory. So I mean, they're loaded from disk to memory. And so the text section where the code, this is loaded, is read-only, because generally, I mean, code is not modifying. There are some sort of self-modifying codes out there, but like in general, code doesn't change during program's execution. So it's generally loaded into read-only memory. Data section is loaded into memory. The BSS section is loaded, and this is our uninitialized variables. So they're loaded into memory and usually initialized to 0, right? Shared library calls are resolved, and so this is the interp, like this is why we have this .interp section. It's telling us, hey, yep, use the Linux dynamic linker, and then if I'm using standard system libraries, it will go and like dynamically link them during system execution and whatnot. And then we'll pass control to the program once it's loaded and we're ready to go into the CPU. So then how do we pass control to the program? And this is sort of like where it gets a bit tricky and complex. But for those that don't really know, that like the standard C library plays a very important role in sort of a computer's execution or like whatever. And then you have like the glibc, which is what like will be found on most Linux-based systems that handle sort of these functionalities, like this sort of calling of kernel functionalities from essentially what's called user space, which is where my programs exist on my graphic sort of layer, right? And so the first step that happens in the process is that there's a symbol that's found in the symbol table of your linked executable file that's called start. And so this is your entry point into your program. And so what this happens is that this start is invoked, meaning that the code at this location in your file is actually executed on the CPU. And in turn, this invokes essentially this libc start main call, which will call, it will sort of invoke the program with some parameters that it pulls from, like for instance, the execution directory, like where the program was called from, and all sorts of other things. It's like sort of a step where it gathers system data to be passed into the program. And then we have, for instance, they will call the init function, which is also a symbol that's exposed by your linked file. And this is where, for instance, initialization code happens for initializing certain variables from, for instance, where from loading values from BSS, right? Finally, once all of this is done, so once your program has been invoked and passed into, like sort of put into the kernel, it's been given these sort of system parameters or system arguments, and all of the sort of global variables and initialization code is done, then the main function is called. So this is this one that we all know too well from writing, if you've written C code, that you have like this main function. And so this is this real proper entry point into where your code starts getting executed. So the rest of this stuff is sort of like initialization code that happens on like a kernel level or on a system level, but your program really starts executing here. So your program will sort of execute and execute and execute until it stops running, until it's terminated and finished executing. And then what happens is there's another symbol called fini, and essentially this is what is called to handle program destruction. And so this will be sort of anything from freeing memory and variables to actually shutting down connections that have been opened up, what have you. It sort of destructs everything that the program has constructed. And then finally, the program exits and it surrenders control. And so I don't know what this link is, what it's doing there. But, so now we know roughly how this happens on a computer. We have our linked file, which has all of these text segments. Very roughly said, they get copied into memory. Then your program gets called. It does some sort of initialization calls, sets up the variables, and then it enters main, right? And then it passes over, it starts executing your code on the CPU until it finishes, and then the kernel will take back control. Now, how does this happen on an embedded system? It's very simple, but the biggest difference is that we don't have an operating system or a kernel that is loading a program in and then we unload a program. Like an embedded system generally has one function and it executes what we would say like one program. It just runs and runs and runs it. Like for those of you that are familiar with like an Arduino, like the really basics of an embedded system, your code will generally exist inside of like a while loop. And so the whole idea of the embedded system is they never stop. They run one functionality for their entire lifespan. And so by doing this, we also then don't want to have on top of this some sort of a kernel, we don't want to have Linux on top of it that's doing sort of complex functionalities. Like embedded systems that run Linux do exist, but if we're talking about really small bare metal applications, such as like small microcontrollers like Arduinos, there's no operating system that's going to load your program. Your program itself needs to just end up in memory and get executed. And so this is how when we have to start relying on making sure that we compile our ELF file into a certain structure and that it gets put into the right place on your little embedded system's memory, such that when the power is applied to the board, it can just start executing the code that it finds in memory. So where on our PC we loaded the program into memory, the board itself or the embedded system, we sort of, instead of loading it when we want to execute our program, we flash the program, meaning we plug in a USB cable and actually transfer the data into the embedded system's memory, such that when the power is applied, similar, like the same as when we run the program on a laptop, the program is in memory and ready to go. So the loading of a program on an embedded system is generally more of like a flashing, in that we burn it into, we don't burn it, but we make sure that it's available in the system's memory, right? And so then where it lands in memory and how it's specifically structured, this is sort of architecture dependent, the microcontroller you're using, and there's all sorts of small details, but I'll just generally sort of try and abstract it now, just saying like in general the concept is the same, is that you put it in a certain place in memory such that when power's on, it just starts executing the instructions that it finds, right? Okay. So I need a coffee. So the boot process in a microcontroller is a lot simpler than you'd think. I mean, obviously there's a lot of complexities to it, but the general process is quite simple. Really what happens is that we turn on our board, we plug it into USB, we turn on the power, what have you, and then there is essentially a routine or a set of like a sort of a little chunk of code, which is commonly called the reset vector. And this is what the first thing that's run in memory. And so your board will have some register in it, which stores the value of the address that should be run first. And then once the board is powered up, it will just start executing from that location, right? And so this reset vector is then executed, as you can see here in the second step. So we apply voltage and it sort of powers up the microcontroller, and then it just starts executing the reset vector. And so on an ARM, on an ARM microcontroller using the ARM architecture, the reset vector will point you to the 0 address on RISC, some RISC chips. It points to like in hex like 8000, I think. You can find them all on Google. It all varies slightly, but the idea is the same, is that you apply power and then some predefined memory location starts to execute. And so in here is this reset vector. And now the reset vector is very important in that here it provides system-specific assembly code, because if we're like, unlike with writing code for our laptops, even if you have a different Intel CPU to me and it's older with less memory and you're running a different Linux or whatever, we have the same architecture. We're all on an x86 system and they can all understand the same instructions and programs. But when it comes to embedded systems, the sort of the functionality, the features, the architecture of these chips changes. There's a lot more variation, and so we need to make sure that we're really writing code that's specific to the architecture. Like when we're talking about STM microcontrollers, they have all the different ranges. They have the F4s, the F3s, the F1s, the F7s. There's like the M somethings or other. No, not M's. L, like the low power series. Like there's all of, they're all ARM chips, but they're all different in subtle ways. Some chips will have floating point operators support, some won't. And so you really need to have this reset vector that's very much specific for the target hardware. Like, is it specifically for the series of chip or the exact model of your chip? This is all sort of up to the implementation of the engineer or whoever's designing the silicon. But this code is responsible for really getting your CPU running. And so this is very low-level code, and it's placed into this memory location that is sort of specified by the hardware architecture. And then you have this linker file, which is a file used throughout the compilation process that makes sure that the final file is structured in a way that this reset vector lands where it should, so that it can be executed when the CPU starts up. And so the combination of like linker file, which is also architecture specific, and the architecture itself means that your code lands in the right place in memory, such that when power is applied, it can start to actually execute code. Now, these linker files and dealing with these registers and stuff, this is stuff that the average embedded engineer will never have to deal with. So I've never written them. They come from the vendors, from STM or from ARM or TI or whatever. They're really good to read through them and to get an understanding of what's going on. But actually writing the system-specific assembly is very rarely required, right? But so now we have we know that we have this reset vector and that it lands in a certain specific location in memory such that it gets executed when the system boots. So, but what does it do exactly? So there are a few sort of things that it needs to do, similar to like when we run a program on our laptops. You know, there's like these variables in memory that need to get loaded or initialized, blah, blah, blah. And so what generally happens is that we have, for instance, the vector tables, which for those of you that don't know, this is sort of like when the interrupts come in, it's a list or it's a table of like the functions where they exist, or like where the callbacks exist in memory. And so this is generally compiled into binary, and therefore it's in flash, and this gets copied into RAM. And so it's done because interrupts will come in all the time, and you want to have your interrupt tables in memory so that they're quick and easy to access. And so they'll usually provide memory locations where all the different callback functions actually exist in memory, right? Similarly, the uninitialized data initialized data and uninitialized data will be copied into RAM. So this is all data that's going to be used throughout your computation. This, you can do things to avoid this. If it's data that doesn't need to get modified, then you could just keep it in read-only memory, and then it might never get copied into RAM to save on RAM usage, for instance. Then you can also, for instance, copy RAM functions. And so generally on most embedded systems, code is executed directly from flash because of keeping RAM consumption down, but you can load functions into RAM for quicker execution. Then, for instance, we'll set up the processor's stack pointer. And so you'll see more about this in you're talking about system architecture. Similarly with the heap, so this is sort of setting up the memory usage, that like how RAM is used by the program for actually performing the operations specified in the program. And then it will also do, for instance, any sort of system setup. And so we'll see in a second that, for instance, on an STM board, or in the example I took, this sets up the CPU's clock. And so this is sort of very important peripheral initialization code that needs to be done such that the CPU operates correctly. So, and then after all of this has happened, so we've set up our data, or we've set up our interrupt vector, we've copied our data we need, we've initialized memory essentially for the execution of our program, we've initialized peripherals and set up the system into a working state, then we can jump into main. And so this is somewhat similar to when we run it on a program, on our PC, we set up memory, or we copy things into memory, or load it into the kernel, into memory, and then execute main. The embedded system just has a few sort of extra things because we're dealing with these low-level systems. We have interrupts and blah, 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 and we have to really initialize the hardware. And so there's a couple of extra steps that go on. So then this here on the left is a section of the startup code. So this is assembly. This is the startup code from an STM32. This is actually the code used by my students at TUM when they do a similar course to this, where they're actually programming STM F4 boards. But if we sort of look through this, this little chunk of assembly, we can see it's doing a few different things. Namely, it's setting up like the stack pointer, which we can't see. This is at the top of this, like this is the file's a lot longer than this, but this little chunk. Generally what this reset vector in this STM board is doing is it's setting up the stack pointer. So sort of saying, yep, okay, when you need RAM to use, this is where you can start taking it from. It sets up this ISR, so this is this interrupt vector. It's allocating if the interrupts are being used, and I have written an interrupt handler function for a certain interrupt, then the address of this function will land in the vector table so that when the interrupt comes in, the CPU knows what function and where it is to execute, right? But then, as we can see here, maybe, no, not quite, it's still not enough on there, there's the reset vector, right? And then so like, the reset handler. And so this is the assembly, like the assembly language label for the function, like the assembly function that goes through what happens during the reset handler, like this sort of boot phase. And so here we can start to see things in the assembly. Copies all require data from flash to RAM. And so here we can see here we're starting to do these loop copy data in it, and this is running this label here. And if you go through this and you know assembly, then you can sort of see that this is recursively copying data. And then we also have, for instance, like filling zeros in the BSS. So it is doing this sort of initialization of the BSS segment, right? And finally, we configure the CPU's clock system and external RAM, SRAM. And this is what happens here in this system init call, which the actual code isn't in there, but it's branching to this system init label. And then after the system init label is returned, like after it's finished executing, it will then branch to main. And so then it's executing main. And so this is a snippet from this system, this startup file. I think I've got the little arrow here where it's saying, yep, cool. And then this is really when it's starting to execute your code. So to quickly summarize what happens on the embedded system again, in that in comparison to your program on your laptop, the program isn't loaded into memory, like it isn't copied into memory, it's flashed onto your board into a specific, or structured in a specific way, using similar sort of constructs to these normal ELF files. You have different sections and whatnot. It's placed into specific, it's structured in a way that when it's placed into a specific point in memory, that when power is applied to the embedded system, it can start executing instructions from this specific point in memory. And this specific point will usually then point it to, almost always point it to this reset vector. And the reset vector is not always the same, but it generally goes through the same process of setting up memory, setting up interrupt vectors, then sort of copying data across from flash to RAM, peripheral initialization, and then eventually it will enter, once the system is completely ready, it will enter your program's code by entering the main function or branching to the main function. So it's not too tricky, and it should hopefully help to sort of demystify a bit this whole process. And it will all become even more clear when you go on and learn more about system architecture and how assembly code is executed on CPUs and all of this sort of stuff. So I hope this helps.